6, and 7. Number 5 deals with the average speed of the methane molecules in our original sample. Commonly shown equation RMS, which stands for root mean squared speed. A little math, you can derive this equation, take the square root of both sides, and you'll find that the speed of the methane molecules in our sample is related to its temperature and its molar mass or molecular weight. And when you do math, you'll get the answer as 762 meters per second squared. A little bit more complete, those are the values you would plug in. So for this equation to work, your R has to be in joules per mole Kelvin, and the value is 8.314. Of course, your temperature is in Kelvin, and your molecular weight, molar mass, formula weight, whatever you want to call that, has to be in kilograms per mole. So you can see that unit-wise, the moles will cancel, the kelvins cancel, and it seems strange with joules and kilograms until you realize that a joule is a kilogram meters squared per second squared, and thus the kilograms cancel and you're left with meters squared per second squared. But when we take the square root of that, the final numerical answer has units of meters per second, which makes sense with velocity or speed. And in this case, it's really speed, since in this sample we don't know the direction. So pretty impressive to know that the average speed of any methane molecule is 762 meters per second squared. For number 6, we are asked to describe the intra and intermolecular forces in all these molecules. Intramolecular means the force within a molecule. Inter means between two or more molecules. And the standard verbiage for these answers, intra, force within a molecule, is either ionic or covalent. Inter, between, which is a function of a molecule's polarity, we're going to describe with 3 words: hydrogen bonding, dipole-dipole attraction, and London. And bear in mind that these intermolecular forces are all attractive forces, as the molecules assume their lowest energy orientations. At any rate, it's helpful to have a remembrance of electronegativity values as given to us by Linus Pauling, and the electronegativities increase that direction on your periodic table. So we find the most electronegative element, fluorine, and the least electronegative would be cesium. And what we don't usually talk about is electronegativities of your noble gases, because they're not really involved in bonding. And if we want to describe the type of intramolecular force simply using electronegativity values, we would just have to say an ionic bond is when the 2 or more things involved in the bond have an electronegativity difference of greater than 1.7. A covalent bond, the difference of electronegativities is less than 1.7. And we further describe covalent bonds as being either polar or nonpolar. And nonpolar, the difference in electronegativities is between 0 and 0.5. Polar, between 0.5 and 1.7. So for example, if we look at part A in number 6, sodium chloride, the electronegativity difference between sodium 0.9 and chlorine is 2.1. That's greater than 1.7, so we say sodium chloride is an ionic bond. And once we know it's an ionic bond, its crystal structure is a lattice where each sodium has connected to it 6 chlorines and vice versa, so that's a very strong arrangement, and ionic compounds are all high melting solids. For the next one, helium, it's not a molecule at all, it's an atom, so we don't have any bonds, therefore we don't really have any intramolecular force, and the intermolecular force is going to be our weakest flavor, London. So that means helium's going to be a very ideal gas because it's light, it doesn't have any bonds, and it doesn't have any intermolecular attractions. For carbon dioxide, first thing we would want to address is a CO bond. The difference in electronegativity between C and O is 1. And that electronegativity difference says that the CO bond has some polarity that we described with those partial plus, partial minuses, and we can also describe with an arrow. When we get to the actual molecule now, we have to take into account that the molecule doesn't have just one of those bonds. If it did, like carbon monoxide, it would be polar, or at least somewhat polar. But with carbon dioxide having a linear shape, when we look at the dipoles using the arrow method, those dipoles move in equal and opposite direction. So we would say the CO2 molecule is covalent and nonpolar. Nonpolar because, again, the dipoles cancel out, and as such a molecule, if we want to know how one CO2 molecule will associate with another, that's again an intermolecular force, we're going to describe it as the weakest of the 3, London. So this one will abbreviate covalent and London. For CH4, playing the same game, the C and H atoms, a CH bond, the difference in electronegativity there is 0.4, so that's going to be not ionic, but covalent, and not polar, but nonpolar. So right away we already know the CH bond is nonpolar, and furthermore, when we draw methane's Lewis structure, we can see that the individual dipoles, which all point towards the partially negative carbon, cancel each other out. So one CH4 molecule, being nonpolar, will have a very weak attractive force, again called London, between 2 molecules of methane. So for methane, we're going to say covalent and London. When we get to HCl, again, as soon as we draw a Lewis structure and see a line, we know that's a covalent bond. We can knock that home by saying H2.1, Cl 3O. So the difference is 0.9. 0.9 falls in this range. So we say this HCl is a polar covalent bond, and it's polarized like that. And be forewarned, you should always include the lone pairs, even though they don't really play into the polarity of that shared pair of electrons that we also call a covalent bond. So HCl has a significant dipole. So how will 2 molecules interact with each other? When the molecules assume their lowest energy state, we're going to have the situation where the positive and negative of corresponding molecules orient to each other so that we can get that attractive force and that attractive force. And it's not a hydrogen bond, even though it's hydrogen atom, because hydrogen bonding can only happen when H is bonded to O, N, or F. It's not London because this certainly is a moderately polar molecule. So we would describe these forces as dipole-dipole attractions. So for HCl, we'll summarize the intramolecular force. That one right there is covalent. And the intermolecular force, those right there, are dipole-dipole attractions. For HF, similarly to HCl, we draw the Lewis structure and we can see 2.1 and 4, so we're at 1.9. You might say it's an ionic bond. Another way to look at it is those two are nonmetals, and anytime we have nonmetals, we're going to call it covalent, but it is a quite polar bond, polarized again like that. And in this case, we do have an H bonded to an F. So when we draw the second molecule and want to describe the attractive force between negatives and positives of sequential molecules, we would call that attractive force a hydrogen bond. And we would call that attractive force a hydrogen bond. So for HF, covalent and H bonding. For NH3, again, we want to draw a Lewis structure, and remember that when you do, the lone pairs are important. So that's a pyramidal shape, and the N to H difference is again 0.9. So each of these is significantly polar, with N being more electronegative than the H's. And so the whole molecule is polar because those don't cancel out when we draw the dipoles in. And so one molecule of ammonia will orient itself to another in an attractive sense, where you can locate the positive of one region of ammonia next to the negative of the other ammonia, and vice versa. And then that's going to be a hydrogen bond, and that's going to be a hydrogen bond. So for ammonia, covalent intramolecular, and hydrogen bonds for intermolecular. Water, you should just flat out memorize. We already said water's polar, water's bent. The OH bond has a difference of electronegativity of 1.4, so it is significantly polarized, like so. And we could draw our arrows. And the next molecule of water will orient itself so that the electronegative O of one molecule will hydrogen bond with the electropositive H of the other, and vice versa with the H and the O. And so we would say water has a covalent intramolecular force and H bonds between the molecule. And this, of course, gives water its unique properties. So covalent and H bonds. Magnesium oxide, we're just going to keep it simple and say if it's a metal and a non-metal ionic bond. Don't need to go into the intermolecular to say anything, because ionic compounds are all high melting solids. Last one for methanol. The key part of the molecule which makes it polar is this COH region, and that's again significantly polar because of the OH bond next to the CO, and those would be hydrogen bonds and those would be hydrogen bonds. So we would say covalent and H bonds. And that also tackles number 7, so I was just asking you to be able to draw two molecules and orient them how they would be shown in an attractive sense. So you could have chosen any of those molecules. And strangely enough, even when we have a nonpolar molecule like methane, there is a very weak attraction between the two molecules, and that's all described by London forces. So to summarize, we want to understand properties of molecules. Specifically, to do that, we need to describe whether a molecule is ionic or covalent, and then how many molecules of the same or different will interact with each other. The greater the strength of the bond or interaction, the more likely the thing is to be a solid liquid and not a gas. And for the purposes of ideal gases, then the most ideal gas in number 6 would be helium. And certainly we can say that any of these hydrogen bonding molecules are not ideal gases.